Okay, so welcome to the Tutte Colloquia. We are very happy to have Robert Hildebrand here today from Virginia Polytech Institute and State University. Robert obtained PhD from UC Davis and afterwards did postdoc at ETH Zurich and IBM Research Center before joining Virginia Polytech. And he works on integer programming and combinatorial optimization. Today, he's going to talk about binarization in IP and mean LP. Robert.
Great. Thank you. Well, first of all, thank you so much for having me. It's an honor to be here and great to talk to all you wonderful people. This is kind of an ideal setting to give a talk in, I think. So I'd like to talk about a few different research ideas and then focus on some recent work. And basically, I want to try to tell a story about how integer variables can interact in a mathematical model and what might be useful in terms of reformulations. So I'm going to talk about some work starting with Jurg and Robert and Rico from ETH. And then I'll mention some ideas from Octa and Sanjeev. And then another approach to MinLP with, so this is Benjamin Beach on the left and Kimberly Ellis. And then we'll conclude with kind of the main portion of the talk, thinking about this work with Ben and Joey Hachut. So that's the plan for today. So I guess you all know what optimization and mixed integer programming is, but let me just give you some pictures to give you an idea of where I want to think about these things. So here we have, oh, you can't see that I changed the screen. There we go, great. Okay, so let's see, my pen's working today. Okay, so we have standard LP relaxations. We'll think about this as like our nice feasible region. And then I want to think about the idea of what happens when you add integer variables to your problem. So of course, you have like the mixed integer version, or you can have the pure IP version. And the origin of the talk is to think about, well, it seems that the LPs are easier to solve than IPs. So how can we try to reformulate a problem to push it towards the LP region? Okay. So we'll think about this first part of, can I reduce the number of integer variables in a model and still like really model the things that I want to model? And somehow, hopefully, that implies something about complexity of solving the problem. And then we'll kind of flip the idea here and say, well, what happens if I do increase the number of integer variables? And can this be helpful when actually solving things? And why could that actually be? Okay, so the first, I guess the second image that I want to show, this is kind of what got me excited about this back in the day. So there's this idea of this, you can take a cube, and if you hit it with the right linear transformation, you get this rotated cube. And then there's this sneaky thing where you can add a single integer variable. So you can ask for just one of the variables to be integer. And the result is that you get all of these actually exponentially many slices that result. Okay. And so if you were to actually look at the convex hull of solutions, look at this mixed integer hull, you see that it's actually a very complicated set because I've introduced a facet for every vertex that I had before. And so originally, well, here we can say that somehow I can produce very complicated looking sets by using a single integer variable. And so the hope with this is then, can we model complicated polyhedra, traveling salesman polytopes, matching polytopes or something, using few integer variables, and then gain some complexity understanding there. Okay, so and why would I do this? Well, if we look at complexity of solving integer programs, so Lenstra told us this in the 80s, and there's been a sequence of results since then, kind of improving Lenstra type algorithms. But what it says is that you can actually solve mixed integer linear programs if you, with some complexity that's polynomial in the encoding size, the number of inequalities, and the number of continuous variables. Okay, and then you have some exponential term in terms of the number of integer variables. This is something you'd call fixed parameter tractable in terms of, I can fix any n and it doesn't change the polynomial dependence on the rest of the complexity. Okay, so this is really nice, and this says that if somehow I can take a problem I want to solve and remodel it with fewer integer variables, then potentially through this complexity analysis, I can have a better complexity of solving a problem. This is the dream goal here. So how might we go about reducing integer variables? And so the approach that we took was, well, suppose I take my optimization problem, and what I'd like to do is simply remove the constraint that my variables would be integer. And then instead, I'm going to insist that some linear transformation of my variables is integer. And here we'll think that k is something much less than n, so that we only have a few integer requirements, and hopefully it still models the same set of points we care about. And so here you can think of this as like your wx. And here you see that we have this like mixed integer slicing happening, and it gives you some sort of feasible region. And so there's a few questions to think about here, like, can I attain the same integer whole if I look at the mixed integer whole? Or can I get some approximation guarantees and improve proximity to optimal solutions? And so I just want to mention this idea, and then we'll talk about some negative aspects here. So the first idea here is, well, we know if we have totally unimodular constraints, then something wonderful happens, and you can say that the convex whole of your integer solutions is the same as the original LP relaxation. That's a wonderful theorem. So what you can do is you can actually extend this theorem, and you can say, well, suppose I have k integer variables, and I insist that I have some linear transformation that's going to be live in my integer space. Under what scenarios can I argue that I will actually get the convex whole? And so one property here is if I kind of stack the original inequality matrix with some version of this W matrix along with some U matrix here, if this whole thing is actually TU, then I recover these nice convex whole properties. So that's one instance, and there's a couple kind of easy applications that this works into. I'll mention there's some nice work by Joe and Robert and Miriam and IPCO last year that extends the usefulness of this approach here. Okay, so that being said, our friends at Zurich also came up with a negative result, which I'll summarize here. It basically says that whenever you have a good mixed integer programming extended formulation, then there's also a good LP extended formulation. So whenever you can do something with MIP, you can also do something with a nice LP in extended space. And this work uses some geometry about the feasible region, and then it uses some approximation results for hardness of approximating certain polyhedral sets. So this was frustrating because I wanted to model things like matching polytope with some few integer variables somehow, because we know matching can't be, there's no nice extended formulation for matching, so maybe we could do it with something MIP related. Okay, so that investigation terminated, I guess, for me at the moment. And as I gave some talks about that, people kind of said, well, when I actually solve integer programs, I like to add variables. And sometimes that's useful. And so I don't know, like, why is this actually happening? Why Lenstra says we add more variables, then the complexity gets worse. So what can we understand from this about adding variables that makes our life easier? And so I'll mention two results, and then I'll get to this idea about some mixed integer quadratic programming. And so the first result, which I just want to express kind of maybe why adding variables helps. So I looked at this with Sanjeev and Oktay, and we asked, so suppose I have a mixed integer linear programming formulation, and I have some general integer variables. Let's try to transform this whole thing so that I can get rid of this integrality and make it just continuous, and then introduce some auxiliary binary variables that somehow cover all that imply my integrality that I want. Okay, so kind of standard ways you can do this. There's some more complicated ways you can do this, but you can always take, a single integer variable and rewrite it in binary with some 0, 1 variables, and then you recover the integrality of x through the binary on z. Okay, I call this a log formulation because it uses only logarithmically many z's in terms of the upper bound u. Okay, turns out you could do this in a different way. You could also think about using lots of binary variables, say one for every value, and one for every integer value between 0 and u. And I call this the full reformulation because we have this coefficient here. And then we ask that the sum of the binary variables is less than 1. And so really you pick off a single binary variable, and it tells you what value of x you're going to take. Okay, so you could try both of these and kind of see what happens. Our kind of encouragement to look at this was this paper by Angela and Van Vee. And what they'd done is they'd solved this transportation problem where they had these xi variables that are integer, and they're supposed to model amount of products being moved from a facility to a customer. And what they'd found was that if you use this full reformulation on all of your variables, and so you just transform them like this, that your integer programming solvers, Cplex, Gbby, tend to run much faster. So something's happening here. There's some structure or something interesting happening. I will mention that if you try to do this, it turns out that the best way to do this is to remove your x's and literally substitute this in your formulations. And somehow this allows Gbby and Cplex to see extra structure in the equations that you were missing if you don't substitute this. Okay, so I'd like to try to explain this phenomenon. And I think the way this comes out, so we don't have great proof of this, but we have some theoretical evidence that this should work. So if you ever go and solve an integer program, you look at a log for Cplex, and you'll see that along the way, you add all of these different cutting planes. So there's all these different types of cuts, and most of them fall in this category called split cuts, which I won't bother defining for this talk, but some of you know what split cuts are at least. But they're a category of cutting planes. And if you don't know what a cutting plane is, so cutting planes, the idea is you, when you solve in a branch and bound tree, you optimize over your LP relaxation, and you end up your LP optimum. And then you ask, how can I add some valid inequality that gets me closer back to my integer points? And these are extremely useful in solving integer programs. Okay, so then the idea is that if I add these integer variables, so we convert from the general integer to these binaries, that possibly there's some strength that's included. And so here's a cute little example that displays how this can work. So suppose I have this kind of very simple polyhedron that's just this little region here. And what I'd like to do is add some cuts until I can reach the integer whole, which is this single point here. Okay, and you can see that in the original space, it requires 2 cuts to do this. So you have to have one cut facing one way and one cut facing the other way. Now, if you add binarization on top of this, so if I take my x1 and x2 variables and I convert them into some z variables, it turns out that in extended space, you can model these two cuts with this single cut here. And so somehow you can actually cut off more things in extended space using these nice cuts. And there's something interesting going on here, that the cutting plane that does this requires interaction of the x2 variable and then something coming from the x1 variable. And so there's not just behavior dealing with the binarization of single variable. There's some interesting structure to be had when you look at the combination of variables from different binarizations. Okay, so, and then we have a theorem that talks about which binarizations are better and which ones can get you better cuts. Turns out the full reformulation can get you, in theory, better cuts than everything else. And some of this practically depends on what type of cuts Gbby and Cplex are using to find. Okay, so that's one idea I want to think about. Cutting planes in extended space are powerful, so maybe this makes sense to add integer variables, as long as you don't add too many. So I'll mention one other place where this has shown up to be extremely useful, and then I'll get to my recent work here. So if anyone's ever studied these pooling problems, there's this idea, there's this large problem where you have these oil tankers, and they're delivering crude oil to ports. And but most of the ports have a number of different tanks where they can mix crude oil in. And the goal would be to mix oil from various tankers such that you get the right chemical composition in the tanks that you want. So once you have the right chemical composition, you can then pass these materials to production, and as long as they have nice properties, production is cleaner and more efficient and more profitable. Right? So there's a big question of how do you schedule these tankers in a way that they bring the right crude oil, put them in the right tanks, and have the right mixing. And this is a very complicated problem that lots of people have studied. And I just want to point out the main source of non-convexity that comes out. And so it ends up that when you try to calculate these chemical compositions, you end up with these bilinear terms between variables. And so here we have a variable that talks about specs or specifications of the crude oil, and then some variable talking about the amount of flow that you're moving from one place to another. And so there's a few different techniques to handle these types of problems. It turns out that a few techniques are kind of similar. And I'd like to point out this idea of how to approximate the bilinear term using some binary variables. And so some people have called this NMDT. So it's called non-parametric multi-disaggregation technique, or at least what I'm going to show you is some similar version to this. And so the idea goes like this. You say, well, suppose on an easy stage, suppose I have a product between a binary variable delta and a continuous variable y. And what you can do is reformulate this quadratic constraint problem in a mixed integer linear version, where I basically apply a McCormick relaxation to this, and then I've linearized the whole thing. And one trick is you can add this extra x bar variable where these things sum to y. Okay. So this is a nice linearization technique, and you can apply this in the more general setting where if you take two continuous variables, you can change their product by, you can discretize one of them. And so use some binary variables to rewrite z in some nice way and just approximate z on a grid. And then now I can look at the product, z times y, and z times y is now a product of y times my alpha variables. And then I can come back and apply this technique here. Okay, kind of a simple idea, but it turns out to be extremely useful in solving these pooling problems, and has helped, I guess, many people solve these types of problems. So we did one of these, a slight variant on this, and then added some like rolling planning techniques that help solve these problems over a long time horizon. Okay, but the point today is binary variables and what we're doing with them. And so I want to share this recent work. Paper was supposed to be on archive today, but it'll probably be on our archive next week after we make a few more typo edits and whatnot. So new stuff, and hope you enjoy it. So, okay, so we're going to look at, for the rest of the talk, minimizing a quadratic function over some feasible set. And you can think of X as being a polyhedron, and that's kind of what we'll focus on. But we could deal with more complicated sets. Okay, and the real interesting scenarios are when this Q matrix is actually not positive semi-definite, which means that your objective is non-convex, and you have to do certain things to try to solve these problems. Okay, so we are applying this idea of a diagonal perturbation. It's been used probably over the last decade or so, a couple of times. And so the idea of the diagonal perturbation is, how can I alter my objective function to make it convex and then handle the non-convexities in a different way? So I'm going to create some diagonal matrix D and then perturb my Q matrix here. And then I have to subtract off the perturbation later, but what I'm going to do is subtract off D times Y, where I've created some new auxiliary Y variables that handle the Y equals X squared part. Okay, so I've now made the objective convex, and my nonlinearities, or my non-convexities, are now in the constraints. And now if we want to try to solve these problems, all we're left over to do is try to model Y equals X squared in a nice way. Okay, so that's what I'm going to do for the rest of the talk. I'm going to talk about ways to model Y equals X squared and hopefully convince you there's some interesting ideas of how to do this. Okay, there's a handful of literature I should probably tell you about. We're going to focus on a paper by Dong and Luo that kind of inspired this idea. And then there's other literature on doing these diagonal perturbations in terms of what are better ways to do these diagonal perturbations, and some estimates on these things. There's also a handful of work I should mention about piecewise linear functions and modeling non-convexities. The main thing I want to mention or think about that I'll talk about later is this paper by Juan Pablo and Shabir and George that create compact piecewise linear formulations. And we'll see how that connects to the formulation we're going to look at today. And I'd like to throw out, I'm going to ignore some great work on mixed integer quadratic programming, on adding extra cuts and other methods. I'm going to ignore Boolean quadratic polytope and all these types of things, and just focus on this one kind of narrow technique and see what we can say about it. Okay, so the inspiration was this Dong and Luo paper. And what they'd done is came up with some large mixed integer programming model that approximates the function Y equals X squared. And so here's the function Y equals X squared. And for different, you can reparameterize the model with different number of layers to get a better complexity. And so this new variable says, how many layers do you want in your system? And at the first layer, if you use no integer variables or no binary variables, you can get a relaxation of the quadratic. That's just this nice triangle. But if you up the number of variables you're going to use, you can get a better or a tighter relaxation that has multiple disjoint parts. Okay. And then if you up the number of layers again, well, you can't really see the green, but there's another green layer in here that shows you have a very close approximation of y equals x squared. Okay, so just kind of show you where this comes from, because I think it's really cute. If you look at this formulation by Bental and Nemirovsky, so they talked about how you can take the second order cone and then approximate it with a polyhedral cone. And they said, well, let's use some continuous variables. And I'm going to have some sequence of continuous variables that then relate to prior continuous variable in the sequence. So you can see the j minus first term is in there, and they're related through these absolute values. And really what this does is it creates a chain of nested absolute values that creates a very complicated function with many facets. And so they were able to obtain a nice formulation where they can use where the number of facets of their cone is actually exponential in the number of variables that you use to create it. Now, the Dong and Luo paper, they kind of took this and said, well, if I slice the cone, then I actually get a quadratic function. That's exciting. I actually get a quadratic function after I slice it with a hyperplane. And so if I slice this polyhedral approximation, then I can pull out a nice piecewise linear approximation of the quadratic. And there's some extra work there in making this. So this is actually an under approximation. There's some extra work in making this an over approximation, so you can actually cover the whole quadratic and make sure you have the right formulation. Okay, so here's an alternative idea of how to get a nice piecewise linear approximation of the quadratic. And maybe someone here has a great idea of where this comes from. There's obviously a lot of structure in the function y equals x squared, and somehow some nice things come out here. So if you consider taking the function y equals x squared, you interpolate it with a line, and then I consider the next best interpolation I can think of. And so I'm going to add a breakpoint at x is 1/2, and then I'm going to draw this nice interpolation here. Now, if I look at the difference between these successive interpolations, between this line and the new one, I get this kind of upside down absolute value function. Okay, so what happens when I do this again? I look for the next best interpolating function. So now I'm going to use the breakpoints at 1/4, 1/2, and 3/4. And there's this green line here. And it turns out that the difference between successive approximations is now the same function, but with twice the frequency. And you'll notice here I kind of snuck in some extra coefficients that scale this, so the function actually goes up to 1, but obviously the differences are going to get smaller as you go. Okay, so stepping up one more time, you see the procedure continues, and you get a higher frequency function, actually at twice the frequency again. Okay, so this was an idea of Uratsky from 2017, and he was really caring about neural networks and how do I make a nice neural network that approximates this function or approximates polynomials in general. And what you can see is that you have a nice kind of composition here of how the error terms accumulate or how they can be created. And thus you can write a little neural network here where each function feeds into the next function, and then you have to sum them in the end to get the right approximation of the quadratic. And here you can recognize this is some form of like a ReLU activation function with just some minor offsets here. Okay, but we're not doing neural networks. What we'd like to do is integer programming. And so you pull out your favorite MIP toolbook, and you ask, how can I model this with integer variables? And so we ask, well, let's create some integer variable alpha that's binary and detects where the GI lives. And then let's try to model this relation that comes from these functions up here. And then after 2 minutes thinking about it, you write down the right MIP formulation for how these things connect. And you can see, if your alpha variable is 1, then this forces the GI variable to take twice times 1 minus GI. And if the alpha variable is 0, then it forces it to take just twice the previous GI. Okay. Okay, so we can write down this formulation, and now we have a nice little MIP model that approximates the quadratic very closely. And I didn't mention the theorem, but the approximation, I guess I'll show some things later, converges very quickly. Okay, so what are some nice things about this? This is a very simple formulation. So you see all the coefficients are super nice. There's no sines and cosines sitting around, and it's very easy to code up, actually. It doesn't have this ideal property. So if you look at the convex hull of IP solutions in the extended space here, these inequalities don't actually model the full convex hull, and that convex hull is a bit complicated, and hopefully we'll get a handle on that soon enough. But what I'd like to show you is a very interesting property. So there's this idea of sharpness and hereditary sharpness that talk about if you project into the original variables, then do you have the convex hull? And this actually holds for our case. And then there's some other nice properties here about kind of like minimizing the amount of area that you use to approximate the function. And then if we get to it, we'll show you some promising computations that seems to be a good way to do things. Okay. Okay, so first thing I want to point out with respect to it being like a simple formulation. So this nice paper by Juan Pablo and friends from 2010, they went through and really investigated different ways to model piecewise linear functions, and they actually did this in higher dimensions. And so they asked, they have the script P for like the number of polyhedra to model different sections of your piecewise linear function. And what they found was a nice model that's compact, where the number of binary variables that you need is logarithmic in the number of sections of the piecewise linear function. And that's precisely the paradigm we're in for this approximation, that the number of piecewise linear portions you have is actually exponential in the number of variables that you have. And now, for a slight comparison, their model requires that you do need a continuous variable for every chunk of the piecewise linear formulation. Whereas in our method here, you really don't need, well, you have continuous variables sitting around, but there's not exponentially many of them. So there's only roughly the same number of continuous variables as there are binary variables here. Okay, so that's one aspect here. I'll talk about the sharpness idea, and I think this is probably the reason it has a lot of power and seems to be working well for us. And so the sharpness idea says, suppose I have an integer programming formulation, and what I really care about is some domain X in Rn, but I write some extended formulation in higher space where I've added some integer variables. And then the question is, what happens when I project just my LP relaxation into the space of the original variables? And we'll call it sharp if after this projection, I actually get the convex hull of what I wanted originally. Okay. Now the next step up is called hereditary sharpness. And this idea kind of stems from looking at a branch and bound tree. So if I were to actually fix one of my integer variables to some value, so we'll look at the projection after I fix some integer variables, do you still retain this convex hull property? And it turns out this is going to be true for our scenario. Okay, so let me show you some pictures and some proof ideas and hopefully some interesting things here. So here is the third layer of our problem here, our model, and the integer projection is actually exactly this piecewise linear piece here. And then what we're going to talk about sharpness, we'll say that the formulation is sharp because when I project out all my extra variables, the projection is actually this nice yellow region, which is the convex hull of my MIP solutions. I have a little bit of a proof idea here. And the idea is basically, if you look at the restriction to some x variable, and then really ask, what happens at the lower and upper bounds here? And can you argue that when I minimize in the y direction in my LP formulation, do I get integral solutions? And so ideally, you should be able to argue that when you minimize down here, you should get an integral solution in terms of the alpha variables. And this works out. And so basically, you can do a counterexample argument or a proof by contradiction, where you can say, if this doesn't happen, then let's create a new G tilde. Let's perturb it a little bit such that hopefully we can work towards integrality. And okay, so how the G tilde works is you have to make sure that it satisfies some of these constraints that are tight based off the previous variables. And so you have to do this perturbation, and then after you do this perturbation, you try to show that, well, my new solution should be less than the original one and derive a contradiction. And I won't go through the detail just too closely here, but basic things you need is that this function is actually Lipschitz continuous with constant 2. And then basically as you do this perturbation, which affects different G values, it doesn't change, it changes everything in the right way that you want. Okay, so that's one idea here. That's sharpness. And I think really the more interesting piece is this hereditary sharpness. And this has some fun connections that happen here. So as I said, hereditary sharpness, what we're going to do is think about branching on some variable and then asking what happens in the projection afterwards. And so what I've done here is labeled my alphas. So for every x, I can pick out the binary string of alpha variables that corresponds to that x. And I've labeled where these alphas lie in the region here. Okay, so now I can think of taking this binarization, and I'm going to ask, let's branch on alpha 3 being 1. And what you see is that I get to keep a couple of these, but then I have to take away a handful of other solutions here. So the branching is really interesting because it removes sections of the domain in some non-convex way. And surprisingly, after you do this, setting alpha 3 to 1 in the LP relaxation, it actually projects down to the right convex hull in the end. So somehow the branching here retains these strong sharpness properties, and that should be useful when iterating through a branch and bound tree. Now, I believe what's exciting about this is that the sequence of alphas here actually coincides with something known as the reflective gray code. I didn't know what gray code was until 6 months ago or so, so this is was exciting for me. But so a gray code is some sequence of binaries that's supposed to map to the non-negative integers. And the important thing about the sequence is that if you look at any neighboring vectors here, they're only going to differ by a single bit. So here you have a single bit difference there. And let's, I don't know, look at this one. And you see that, okay, so this one has a single bit difference there. So somehow these neighboring vectors are very close to each other, and that seems to be a strong property. And surprisingly, this gray code, this gray code connection is also apparent in this piecewise linear approximation as I talked about before. Okay, so it seems to be maybe a nice way to get to these logarithmic things. So let me describe kind of how you build a gray code, and then you'll see that it really connects in this way. So if I were to figure out the gray code for number 0 and 1, we can just use a single bit and go 0 and 1 here. Now, if I want to step up to the numbers 1, 2, and 3, what I'm going to do is take my 0, 1 gray code here and map this to these bits here, and then tack on some zeros in the front. And then from here, we go to the reflective part. So I'm going to take this part, reflect it, and I get a 1, 0. And I'm going to put some 1s in front of there. And now when I build the gray code for the next step up, I do the same operation. I take this piece, set it up here, reflect it, and you get the reflection, and then you have your 0s and 1s here. Okay. Okay, so this actually connects very nicely to the way that the G's and the alphas connect, because we have this flipping based off of whether the G's were above a half or less than a half. And you can go through and argue that these things work out in the end. There's also a nice connection to the standard binarization, but I'm going to skip this for the time being, just in terms of time, so I can get to the meat of the proof idea here. Okay, so consider you're running a branching tree here, and you're going to look at your second variable and ask, let's branch on your second variable, and let's set it equal to 0. So what happens when you do this? Well, you lose all of these possible gray codes in your sequence, and you can cut it down to something nice and small here. And what you can see is that it actually becomes a gray code sequence for a smaller set of numbers. Okay, so there's a kind of a hidden gray code sequence here. And alternatively, if you were to branch on the variable equaling 1, you get rid of all these other rows. And okay, so you don't quite get a gray code sequence here, but if you were to take the column that's right after the branching variable, so here I remove the branching variable here, and I actually flip all the bits from 1s to 0s and 0s to 1s, and then I retain this gray code solution here. So there's really a hidden gray code sitting underneath each branching piece here. Okay. So the proof sketch, it gets a little technical actually to do all the computations, but that's really the main motivator for how this proof works out, that the hereditary sharpness works. I won't go through lots of details for the proof sketch, but you can take a look at the paper later if you're interested. Okay, I have a couple minutes. I want to tell you about some area stuff, and then I'll mention computations, and then we'll be done for the day. Okay, so far I've talked about a quadratic function and then having some piecewise linear approximation and what that does. And what I'd like to do is come back to this idea of actually covering the whole quadratic with some polyhedra. And so you can modify the approach in a nice way. So instead of having equality here, I can ask, as the piecewise linear function is just an upper bound. And then I can add some lower bound where I just basically subtract the error of the approximation. And this gets me a nice lower bound in the formulation. And then we can add a couple of extra inequalities to make it nice and symmetric in the end. Okay, so we get the same picture kind of as before, the Dong and Luo stuff, where you can have the sequence of McCormick relaxations of pieces that model the piecewise linear function. Now, okay, and there's one extra piece here where if you want to modify this, and instead of having a single inequality, you add the inequality from each layer of your formulation, you can actually get a tighter approximation. So you have to decide if you want to add linearly many inequalities to help this be tighter in the end. Okay, so you can go through and do some calculus here and compute, what is the actual area that we're getting when we cover this function here. And I won't go through the math, but the area looks something like something cubed, so cubic term of the difference between pieces of your piecewise linear approximation there, or of your McCormick relaxation of that piece. And so what you can argue about our approximation is that because the breakpoints are uniformly spaced in the approximation, given this area computation, it actually optimizes or minimizes the amount of area that you need to cover the thing. Okay. So this is somehow an optimal formulation in that sense. And what we did is compared areas to the prior formulation as you increase the number of layers. And what's nice about our formulation is that for every extra layer, you always decrease an area by a factor of 4. So it tells you how close your approximation is getting. Whereas if you use this other approach, you're not always decreasing by a factor of 4 with each layer. And again, it depends, a little bit where you want the function to be, but I guess this shows that ours is converging slightly faster. And maybe interestingly, if you transform the function to a different area, so instead of between 0 and 1, you say like -2 to 1, you can see that our approximations still converge in the same way, whereas the other approximations don't converge quite as fast. Okay, so I got just a couple minutes here. I'll tell you about computations and say they're promising. We've looked at a handful of different pieces here. So we're going to measure like time and gap and best dual bound produced and whether things time out or not. And we tried to compare as many things as possible and do this in different ways. So we've looked at Gbby and Baron and Cplex, and we've given them different versions of our formulations. And so here's the computational results, which I'll summarize in 3 separate tables. One kind of like the easy instances that everything's solved, one of the instances where things are a little harder and only some of them solved, and then the last one where just the problems are unsolved. And so you can see on the easy instances, most everything does pretty similar on the easy instances. There's not a lot of exciting things to say. On the kind of what we call contested instances, the ones where some solved them and others didn't, we see some nice improvement here. Our time is usually smaller than some of the other ones at least, and the gap seems to be pretty favorable, at least in comparison to some of them. And notice Cplex actually does a stand-up job here. They're doing a really great job on these instances. Okay, and then I guess the exciting part is when we get to the harder instances here. So these are the unsolved problems. And it turns out that our method here does a great job of creating good dual bounds and very quickly. And so here we have our column of like which ones gave the best bounds, and R seems to do most quickly give these best bounds. And so we've tried a couple different ways. We tried to mitigate issues of like pre-processing on the other solvers, and we think we gave a pretty fair comparison here. And also I'd like to point out, we didn't do anything fancy in the coding, so we really just coded up the formulation and plugged this in. And so there's probably a handful of other tricks we could do to make this more efficient in some way. So for instance, maybe some sort of adaptive refinement on the number of layers that you need. Okay, great. I guess that's all I want to say about that. There's some future work to think about. And I guess in the last minute here, I want to say that I'm working on some open source stuff. And if you have materials or things you want to contribute, I would be very happy to hear from you. And so I created this website, which I call Open Optimization, and it's got a GitHub repository or organization connected to it. And so the goal is here, create a nice repository of open source lecture notes, slides, figures, and optimization code, where everything is under a nice license. And there's lots of nice material in terms of the LaTeX and the ticks for generating content. And there's a few projects that are here already. So Leo and Taman and Timothy put up some books, and this is I'm working on a manuscript for operations research. So the sources are online if you want to borrow, remix, steal examples or whatever you want for your own content or classes. And then the last part of this is I'm trying to build like an image gallery. So some of us spend a lot of time making nice images. And if you have nice images that you're interested in sharing, you can upload these things to the gallery, and then everyone can have pretty images for their talks. So we'll see that we have like the PDF, and then the tech files are here too. So if you want to borrow these, maybe you're studying extended formulations or KKT and you want a nice image or something. Okay, that's all my talking. Thanks for listening.
Well, thank you, Robert, for a nice talk. Any questions for Robert?
I'll ask a question. Robert, do you want my image?
Oh, I can, I guess you get highlighted in Zoom.
As an
Oh, yes.
I'm just joking. Okay. Poor joke. Okay.
Please.
So in terms of, you mentioned adding all these extra constraints, and it's sort of a mystery about why that helps in Gbby and C++. Have you thought about duality at all? Because the more constraints you add, the more dual variables you add. And duality is so important because you're really solving, in my opinion, you're always solving the dual problem because of perturbations. So you really, more Lagrange multipliers you have, the better you may do. So that's a long question, but there it is.
Okay. You think that the extended formulation would have a stronger dual to create good bounds? Interesting. Yeah, I have not thought about that at all, and that's a great idea. Thank you. Yeah. Yeah, I guess that somehow plays a role in like the cutting plane stuff we talked about in the IP, where somehow you can find better cuts when you look at this extended thing. And so, yeah, there should be something interesting to say there.
Okay, other questions?
Okay, I'll ask another one. Or is anybody else asking?
Not yet.
No. Okay, when you mentioned the perturbation with the diagonal matrix D,
Yeah,
the quadratic, yeah. So that's a problem that I think it's equation 8, 9, and 10 or something way back.
yeah, yeah. We haven't. I think we looked at a couple different perturbations, and we haven't explored that extremely thoroughly yet. And we know that there's a handful of other papers out there that looked at the diagonal perturbation.
Yeah, there's like tons of papers and actually papers proving the equivalence of different. So you have a diagonal perturbation.
Yeah.
But you can also think about trying to look at a spectral perturbation. And you can prove actually that a lot of these are equivalent. So if you go and take a look at the best diagonal perturbation, subject to, of course, you need some sort of normalization on the diagonal to make it like the sum being constant. And if you look at a spectral perturbation, the best spectral perturbation, the best diagonal perturbation, you can prove these things you can prove that these things are equivalent.
Well, I guess so. We did look at a spectral perturbation, and we computed these things. We did like a linear transformation, and then did a perturbation. And basically, what we found is, okay, so if there's only a few negative eigenvalues, or if you forget about negative or positive, but if there's only a few bad eigenvalues, then this approach is killer and works really well because you only have to model a couple different quadratics. So that's great. It turns out that most of the instances we looked at, it's pretty consistent that about half of the eigenvalues are positive and half are negative. And so we weren't gaining a whole lot from doing a spectral perturbation. And so that's why we came back to this. Also, like the numerics get a little worse after doing this transformation. But yeah, there's definitely something to say for, low rank, like concave quadratics or something. So if you have only a few bad negative eigenvalues, then things get really nice. But I don't know of the application set that makes sense to study. And for some reason, all the instances we look at, it's pretty consistent, about half and half.
So you can say things like the best D to make Q plus D positive semi-definite, subject to the diagonal of D being a constant. You can prove theoretically that that's the same as trying to find the best lambda such that Q plus lambda I is positive semi-definite. So you're looking at the smallest eigenvalue.
Okay, so you're saying that we only need one.
Yeah, maybe I can dig out the theorem. Maybe I don't have time. There's some really, yeah, so like you said, there was a gang working on this ages ago.
Yeah, we looked at some of those things. And I think what the literature was telling us was to solve some SDP, which is what we do. We hand it to Mosaic and it solves an SDP. Whereas the lambda I version, basically what happens is that the range of the new Y variables was too large, and it makes it requiring a much closer approximation. Whereas some of the literature says if you solve an SDP, you can try to reduce the range of these variables, and then this makes the approximation a lot better. But yeah, thanks for mentioning this.
Yeah, I'll send you I'll send you the reference for what I was talking about.
Okay, great. Thank you. Yeah, there's
other questions? Sorry, Robert.
You're great.
I was wondering one thing about, I guess, the numerics in terms of computationals, the computational results that you get, because I think some of these formulations that you were mentioning have some kind of big numbers, right? So how do you deal with numerical problems there? Or are there issues there that you need to be worried about?
I guess you're asking what these like sines and cosines in the formulations, or
yeah,
or
the 2 to the something numbers, right? And these numbers.
That's a fair question, and to be honest, in the results here, I don't know if I mentioned it somewhere, but we're only using 3 layers at the moment, so it doesn't blow up too much. I think we've tried it with more layers, and I don't know that we've explored numerical issues that come up. But even with 3 layers, we get a pretty fast formulation and pretty good balance. Yeah, good question.
Also, I guess one extra thing I was wondering about, again, in terms of, I mean, you have some positive results like computationally, but not only in this, but when you're sort of reformulating in the second part of your talk, right, with adding integer variables. You're attributing part of this also for cuts, I guess, in the second part particularly. But is it also because there is, I mean, it sort of is this, I think, SOS type 2 type of constraint, or type 1. I always forget which one is which, but is that, I mean, partly also why these things work well?
So
as you're reformulating in a way that solvers have been trained to deal with that particular type of constraint and so on.
Interesting. I don't know what solvers do to handle what they do special about the SOS2 constraints. I know that you can pass the solver and tell it SOS2.
Yeah.
A lot. What I get from Juan Pablo's work in 2010 was that theirs was really a compact formulation that was better than the standard SOS2 reformulation.
Okay.
And with ours, as I said, like you get the same benefit of logarithmically many binary variables, but also only a few continuous variables. What I think is the crux here, I don't know how big a role cutting planes are playing in this mixed integer nonlinear realm, but I think that the sharpness has a lot to do with it, and in particular the branching schemes that are possible. And so usually when you solve MIQPs, you do like a spatial branch and bound. And so you end up cutting up the region. You end up cutting up the region in two directions here. And with this binarization, it allows you to branch in ways that cut up the region in different pieces. So like you can branch on, well, this is an interesting case where you somehow separate these pieces into different areas here. And I think what this allows you to do, if you're thinking about like maximizing a quadratic on a box, what you really care about is like the endpoints, the quadratic. And so somehow here you're like cutting out the interior piece and you can move towards the endpoints. So that's my intuition. And I guess some rigorous analysis of what the solver is doing will help expose some of that.
Okay, thanks.
I think we'll leave the further discussions in the virtual grad house time. So let's thank Robert again for the interesting talk.
Great, thanks for having me.